Okay, we're continuing on with our study of momentum and how it's changed. So here in number 9, again it's an N, impulse is causes and is equal to the change of momentum. So J impulse is equal to delta P, change of momentum. Now it's not equal to the momentum of the object, it's equal to the change of the momentum. 10, calculate the impulse experienced by in different cases. Now, we either need, for impulse, we need to know the force times the time, or we need to know the mass times the change in velocity. Because, again, impulse will be equal to the change in an object's momentum. And momentum is mass times velocity. So we have a mass here, 65.8 kilograms. We have a force of 1,025 newtons, and we have a time of 0.350 seconds. So we do have force and we do have time. So I'm going to use the force times time to calculate the impulse. 1,025 newtons times 0.350 seconds will give us an impulse of 359, rounded off to 3 significant figures, and that's newtons times seconds. Now, a newton times a second is the same as a kilogram times a meter per second, because, again, impulse is equal to the change in momentum. A 0.168 kilogram tennis ball encounters a force of 126 newtons that changes its velocity by 61.8 meters per second. In this case, I'm going to find the impulse by determining the change of the momentum, mass times change in velocity. Now I'm going to do that because I don't have a time to go with the force, but I do have a mass to go with the change in the velocity. See, it changes, so this is actually delta V. So 0.168 kilograms multiplied by 61.8 meters per second will give us a impulse of 10.4, again, now Newton seconds, or kilogram times meter per second. They are equivalent units. Now, it doesn't tell us which way it changes its velocity. We don't know if it's sped up or slowed down. All we know is that it did change its momentum by that much. Okay, so now we have some pictures to help us out with this idea of change. Now, physicsclassroom.com likes to use capital I for impulse. Again, most situations, J is the more commonly used. Now, in this one we have 7 ball. It's moving at 0.1. It's got a mass of 0.1 kilograms, moving at 4 meters per second. So it has a momentum of 0.4 kilograms times meter per second. Afterwards, some collisions occurred, it looks like, with an 8 ball. It's now moving in the same direction, the hash marks indicate, at 1 meter per second times, multiply that by the mass of 0.1 kilograms, it has a momentum of 0.1 kilogram times meter per second. Now, since it started at a 0.4 and it went down to 0.1, it has a change of momentum, a loss of momentum of 0.3 kilograms times meter per second. Now again, impulse is equal to the change in momentum, so the impulse is going to be negative 0.3, although since it is an impulse, we'd usually write that as Newton times second. Okay, a moving medicine ball gets caught. Its initial momentum is 10 times 6, or 60 kilograms times meter per second. It's undergoing an impulse of negative 50 newtons times second. That means its momentum is going to change by negative 50 kilograms times meter per second. Now it started at 60, it's going to change by negative 50. We're going to take away 50, so we're going to be down to a positive 10 kilograms times meter per second. Now if it has a mass of 10, 10 times what gets us to 10? Well, 10 times 1 gets us to 10. So it's gone from 6 meters per second down to 1 meter per second. Okay, we can look at that in terms of a car. We can trace the motion of a car. This is typically how you would drive. If you're starting at rest, your momentum is going to be 0. You're going to apply some force with the engine to get the wheels of the to drive against the road. You're going to apply that for some time period. That's going to give you an impulse. In this case, force times time will give us an impulse, J, of 4,000 times 4, or 16,000 Newton seconds. Now our change of momentum is also 16,000, just kilograms times meter per second would how I'd write it. Now we started at 0, we had a change of positive 16,000, so now we'll be up at 16,000, up to 16,000 kilograms times meter per second. Now you're not satisfied, you want to go even faster, so you apply an impulse, another force of 6,000 newtons for 3 more seconds. That's going to give us an impulse of 18,000 newtons seconds, which means we have another gain of momentum of 18,000 kilograms times meter per second. Now we were at 16,000, we added an additional 18,000, so that's going to give us 34,000 kilograms times meter per second. Now we are braking from there to a stop. That means our momentum in the end is going to be 0. We went from 34,000 to 0, so our change of momentum is negative 34,000 kilograms times meter per second. That means our impulse is negative 34,000 Newton seconds. Now our impulse is equal to force times time, so the time is going to be equal to the impulse divided by the force, which will be 34,000 divided by 8,000, which would be 4.25 seconds. I'll round that off to 4.3 for 2 significant figures. Okay, so we sped up again. We applied a larger force, which meant we came to a stop in a smaller period of time. You're just changing the momentum of the object by applying forces. Same thing could happen to a tennis ball as it's bouncing around. Again, it starts at the beginning, it's stopped. We apply a force like with a tennis racket of 60 newtons, 0.1 seconds. That gives us 6 Newton seconds of impulse, which means we've gained 6 kilograms times meter per second of momentum, which means we'll now be up to, since we started at 0, now we're up to 6. Okay. Now the ball is currently moving to the right. As it's hitting the moving to the right, it then hits a wall and comes to rest. That means its momentum is going to be 0. Therefore, the change of momentum during that time is negative 6 kilograms times meter per second, which means the impulse is negative 6 Newton seconds. Those two must always be equal. It's the concept of impulse and momentum, change of momentum. Again, the impulse is equal to force times time, so if we want to know the force on the wall that's on the ball, we'll need to divide the impulse of 6 by a time of 0.05 seconds. Now it is negative 6, so it's going to be negative 120 newtons. So notice it brought the ball to rest in half as much time, so we ended up with twice as much force as we had on the first hit. Now the ball is going to rebound. It's going to be compressed by the collision, and then it's going to use its own internal strength to rebound off the wall, and therefore it'll be moving to the left. Now in this case, we're saying that the ball acts with the same 120 newtons of force, but only for 0.04 seconds. It's not. It's lost some energy there in the action that occurs, and therefore it's only 4.8 Newton seconds. So 120 times 0.04, force times time will give us the impulse of 4.8. 4.8 kilograms times meter per second. Now the force of the wall, again, the wall is going to be pushing to the left. That's really negative. That means these changes are going to be negative, or to the left. Notice that it's now moving to the left. It was at 0. It has changed its momentum by 4.8 in the negative direction. So now it's moving with a momentum of 4.8 kilograms times meter per second. And again, that negative sign doesn't mean that's smaller per se. It means a direction. It's moving to the left instead of moving to the right. Okay, so that's impulse and momentum. Again, impulse is equal to the change of momentum. Impulse is a force times the time. Momentum is mass times the velocity.